Hi everyone, my name is Fasel, and today I'm going to present you our recent paper, Data-Driven Nonlinear Aeroelastic Models of Morphing Wings for Control. This is joint work with Nicola Fonzi and Steve Brunton, and we published the work in Proceedings of the Royal Society A. So the goal of this work was to develop aeroelastic models of morphing wings, and the approach that we chose is based on the dynamic mode decomposition with control. And the idea is to define models for morphing wings that are also suitable for control. So the idea of morphing wings is that we want to improve the performance of a flight system by enabling adaptability over a large operating conditions. And the best example for this can be found in nature, where, for example, here a falcon perfectly adapts its wings throughout this hunting maneuver. So it starts with a high aspect ratio gliding, and then enters a teardrop dive to maximize its flight speed, and finally morphs its wing to this M-type configuration to generate strong wing and tail vortices to improve the maneuverability for prey capture. So the bird perfectly adapts its wing shape throughout this hunting dive by morphing its wings. And our goal is now to also achieve similar adaptability with our engineered flight systems. And of course, we are not exactly there yet, but there is a lot of research ongoing in the morphing wings community. So what you can see, for example, in these two videos is recent work from CMASLab at ETH Zurich. In the top video, you can see a 3D printed composite morphing wing. And on the lower video, you can see a distributed compliance lattice structure morphing wing. And the goal of both of these wings is first to replace conventional ailerons by using morphing for roll control. And then in the case of the upper wing, we basically placed compliant ribs over the full wingspan to be able to change the span-wise lift distribution at different flight conditions and operating modes. And one main challenge of developing morphing wings is that they are inherently flexible. So there is a tight coupling between the structural and the aerodynamic response. And that's pretty difficult to model, and especially also to control. So the goal is here to find accurate and efficient models for morphing wings that are then also suitable for control. Modeling of morphing wings or flexible wings in general is not something new, so there's a lot of research, or there was a lot of research over the last decades, and there is still a lot of research ongoing. So, for example, what you can see in this animation here is a really cool work done by the group of Professor Palacios. They analyze mainly very flexible wings and wind turbine blades. And what you can see here in this animation is a T-tail high-altitude, long-endurance vehicle that is encountering a gust. And they simulate this very flexible aircraft using their simulation toolbox, SHARPy, where they model the wing structure as exact beam elements and couple this structural model with an unsteady vortex lattice method. And in the case of modeling morphing wings, we use a very similar approach. The big difference in terms of modeling the structure is that additionally to the flexibility, like the bending and the torsional flexibility of the wing, we also want to model the cambering of the wing, so how the airfoil actually changes. And therefore, instead of using beam element or an exact beam element method, we use a more detailed shell element-based finite element model. So what you can see here in this figure is an exploded view of our high aspect ratio morphing wing with the top wing surface, the bottom wing surface, and the internal structure. So the internal structure consisting of the two spars and the ribs. And in this case, we have rigid ribs at the inner part of the wing, so from here to here. And on the outer part, we have the morphing ribs, so the compliant structure that replace the ailerons. Then, similar to the unsteady vortex lattice method, we use a 3D unsteady panel method. So we also reduce the problem to the surface of the wing and the wake. And ultimately, what we solve for both methods is a set of nonlinear differential algebraic equations. And this is very important to consider if we then later want to develop a reduced order model. But ultimately, what is the issue with this is that those methods are comparably efficient, but they're still way too slow to be used for control. So we want to develop a data-driven reduced order model of our morphing wing that would enable us the model to be used for control. And specifically, we use the method dynamic mode decomposition with control, DMDC, and we introduce two extensions to this model. The first one is we introduce a formulation to handle the algebraic equation. So this is fundamental, as I said before. That's basically the equations that we solve. So we need this extension that DMDC can also handle these algebraic equations. And then second, we are interested in developing a reduced order model that is valid over a large operating regime. And therefore, we introduce an interpolation scheme that can connect several ADMDC models so that we then finally end up having a parametric ADMDC model that is valid over a larger flight speed range or operating range. And to start with, I want to introduce what dynamic mode decomposition actually does. So first, in DMDC, we need to collect data. So what you see here is, for example, the flow around the cylinder. We run a numerical simulation, and at different time steps, we take snapshots of our state of interest, in this case of our flow field. And in the case of flexible wings or of our morphing wing, we are mainly interested in the wing deformations and the pressure distribution on the surface of our wing. So we're not exactly interested in what's going on in the flow around the wing, but we really want to know what's happening on the wing. And therefore, we define the state of interest for the morphing wing as the wing deformations and the singularity strength on the wing surface. And in case of the wing deformations, we don't look at the actual wing deformations, but we look at our modal coordinates already, so at the structural vibration and morphing modes as our coordinate system for the deformations. Okay, and in terms of the inputs of our model, we basically have two sets of inputs. First, the wing flight states, so the angle of attack and the rotation rates. These are like the first four inputs. And then second, the morphing inputs, so how we actually deform our wing. So when you think about the videos from the previous slide, in reality, we place, for example, servo actuators or some type of actuators to really camber, so deform our wing, and those are inputs to our model. And then we run a simulation, so we impulsively excite our inputs, and we take snapshots at the different time step, and then in a second step, we organize our data. So we have our snapshots and we place them, or we kind of like organize them in three matrices. X consists of the snapshot at time step 1, time step 2, etc. X prime are the snapshots of our state shifted in time. So the first column is the snapshots at time step 2, then 3, etc. And third, we have our input matrix epsilon that consists of the inputs at time step 1, 2, etc. And then what DMDC does is it finds, or it tries to find, a best fit linear model that advances our state X into X prime, considering the inputs epsilon. And ultimately, we want to find the two linear operators A and B. And how this is done is by first reformulating this into X prime. So X prime equals psi, which is our unknown operators, times sigma, which are our known snapshots. And then by using an SVD, we can take the pseudo-inverse of sigma and solve here for psi. And that's how we can get our best fit linear model using this data. And then in the case of our algebraic system, what we need to do is we need to consider those algebraic terms. So what we do is that we not just find the best fit linear model advancing X into X prime considering the inputs, but additionally we also consider our algebraic terms, so our time shifted inputs. So basically epsilon primes is similar to X prime is that we shift our inputs by one time step. So our first column will be the inputs at time step 2, then 3, etc. But then, apart from that, we can apply exactly the same method like in DMDC. So we reformulate this formula here. So X prime equals psi times sigma. There it is. We take the pseudo-inverse to solve for psi, and we have our best fit linear model. Okay, and then having this model, we can look at the dynamics. So we can reshape basically our dynamic modes. So we can take the eigenvalues, or approximate the eigenvalues and eigenvectors of our system, and then reshape the eigenvectors into, let's call it like eigen-wing shapes and eigen-singularity strength with the corresponding time dynamics. We can then, that's basically what we want to have, predict future states, so we can advance our state X into X at time step n into the state X at time step n plus 1, considering our inputs and our algebraic terms. And then the last thing, very important, is that those states might be comparably high dimensional. So this model might still be very slow and not be applicable for control. So actually what we do is that we never really need to calculate those large matrices A, B, and F, or combined the matrix C, but we directly project it onto the dominant modes, SVD modes, of our output space X prime. And this gives us then a super compact reduced order model of our dynamics. So basically we can directly, without ever calculating psi, get our dynamic matrices, or the operators A, B, and F tilde. And what is really nice about this method is that we can still go between those reduced states to the full physical states by using our dominant SVD modes of the output space X prime. Okay, so this is how we define and build our DMDC or ADMDC model. Then in our paper we show, or we apply this to 3 examples. First, a generic differential algebraic system of equations, where we show that it's not only important to use this algebraic extension to get accurate results, but if we don't use this extension, we get unstable system dynamics. Second, we apply ADMDC to aerodynamics only problem, so to a NACA 0012 rigid wing. And then finally, we apply the method to our morphing wing. So as I mentioned before, the state of interest is the wing deformations and the singularity strength, and the inputs to our model are the flight state, so angle of attack, 3 rotation rates, and the morphing actuation. And then in a first step, we train our model, so that's basically the 2 steps that I mentioned before, so collecting data and organizing data. So we impulsively excite our inputs in a random order and take snapshots of our state. Then we can build our ADMDC model, and we then have 2 test cases. So first we test our model by using sinusoidal inputs with different reduced frequencies in the direction of the different inputs. And second, we use a different, like a random set of impulsive inputs in the direction of our inputs. And with those testing phases, what we basically want to do is we want to compare our full and reduced order model. So what you see here in this plot is first the lift coefficient, then the drag coefficient, and the roll coefficient. The yellow continuous line is the reduced order model, and the blue dashed line is the full model. And what we get is like really excellent agreement between the full and the reduced order model. And on top of that, we get a speed up of 3 orders of magnitude. So our reduced order model is super accurate and also super fast. Okay, so so far I showed you results for a single reduced order model, so a model that is valid at a specific operating condition. But as I mentioned before, we're actually interested in developing a reduced order model that is valid over a larger range of operating conditions. So what we then basically do is that because we have those super fast compact models, our idea is to simply run several local reduced order models in parallel, project the local reduced state up to our full physical state, and then interpolate the physical state. So what we do is we have our inputs. Then in this schematic we have 3 local models, so 1, 2, 3. And then for each local model, we advance our reduced state Q at time step n to Q at time step n plus 1 by considering the inputs and the algebraic terms, and then project the reduced state up to our full physical state, and then interpolate the full physical state at our operating condition of interest, so in this case at the flight speed of interest. And that's basically it. That's how we interpolate several local reduced order models. We then also test this approach using the similar set of inputs. So first different sinusoidal inputs with different reduced frequencies, and then the impulsive inputs in a second testing phase. But compared to the plot that I showed before, additionally here we sweep over a velocity range. So basically we accelerate our wing from 35 to 80 meters per second. And again, we get excellent agreement between the reduced and the full model. And even introducing this interpolation, we still get a speed up of 3 orders of magnitude. So then last, to show the performance of our modeling approach, we incorporate the ADMDC model into a model predictive control framework, and we run several control examples. So for example, we try to mitigate gusts, or we try to follow a specific lift coefficient trajectory. And then ultimately, we want to use our ADMDC model to control the loads on an airborne wind energy drone. And what an airborne wind energy drone is, it's basically a tethered drone that is used to harvest wind energy. And the idea of using this ADMDC model predictive control is to be able to fly closer to the maximum wing loading and closer to the maximum tether loading, so that we can basically improve the performance of this airborne wind energy system. And in our paper, we show that we can indeed reduce gust peaks of such an airborne wind energy drone. Okay, so to summarize, we developed a data-driven reduced order model of a morphing wing. We showed its performance in terms of accuracy and speed up, and we also applied or used the ADMDC model for model predictive control. You can find the link to the paper in the description of the video below. You can also find a link to Nicola's GitHub for the code. And additionally, I added some links to the work of Professor Palacios and to the work that we recently published at CMASLab in terms of morphing wings. Thanks for watching.